Hello everyone, my name is Bolin Dai, and I am presenting state-constrained stochastic optimal control using LSTMs. In this work, we consider the system with dynamics as shown in the first equation, under the costs shown in the second equation. The state constraint is given such that CSX can be a nonlinear function of the state. Also, control saturations are taken into consideration. For details regarding this formulation, please refer to our paper. To solve this problem, we first incorporate the constraints and saturations into the cost function. Then the problem can be written as a forward-backward stochastic differential equation. We then use the deep FBSDE algorithm to find the optimum control at each time step. This approach is easier to scale to high dimensions and helps with reducing the approximation error in both the value function and system dynamics. To incorporate the state constraints into the cost function, we can use a penalty function. The penalty function we choose in this paper is given as px. Additional to the constraint boundaries, we have an additional variable k regulating the steepness of the constraint boundaries. Also, we can substitute the quadratic control cost with the cost shown in the bottom when considering control saturation. After including the state penalty and control saturation, we have the new cost function as shown in this slide. We can write the problem in the form of a forward-backward stochastic differential equation, where the control at each time step is a function of the partial derivative of the value function with respect to the state, Vx. We use a neural network to learn Vx when given the current state. During training, we use a L2 loss between the terminal cost and the estimated cost to go at the final time step. And we use LSTMs, which are chosen to address the cursive dimensionality, non-linearities, and long time horizons. We found that starting with a steep penalty function creates numerical instabilities. Therefore, we prefer to increase the steepness gradually. We use the square root of variance of the cost of each run over a fixed number of iterations as the update threshold. We perform these updates until the state constraints are respected by the learned controller. We show the efficacy of our approach on a cart pole swing-up task, where the cart position and cart velocities are constrained to be within a region. We see that our learned controller is able to swing up and balance while respecting the constraints. Also, we see that as we increase the steepness of our state penalty, the velocity curve gradually retreats into the constraint boundaries. To show that our approach is also able to deal with nonlinear state constraints, we limit the total energy of the system, which is the sum of the kinetic and potential energy. We see that our learned controller is able to respect the constraint boundaries. Thank you for listening to this presentation, and for more information, please refer to our paper.